Well, hello Internet, and welcome to part 4 of my time series analysis tutorial series. In this part of the tutorial, we're going to talk about Holt-Winters, which is basically going to lead us down the path where we will begin to be able to predict the future. And I have a lot to do, so let's get into it. All right, so I have the same exact imports I've been using for this whole tutorial series. So as long as you have those, you don't need to worry about it. And of course, there is a link in the description on GitHub. You can get all of this stuff. Which brings us to the Holt-Winter Method. Now, previously, we have talked about exponentially weighted moving averages, which is part of the Holt-Winter Method. And what we did there was we applied smoothing by slowly decreasing the influence of older data. The Holt-Winter Method is actually going to model 3 aspects of the time series, being the average, the trend, and the seasonality, all things I've covered before. And in doing so, it tries to predict the future, provided the series is seasonal and somewhat repetitive over time. But of course, to get accurate results, we must use good parameters, and I'm going to talk a lot about those. So for example, as just one simple example, let's say you're looking at your data, and for seasonality, it may seem that a day represents a season. However, if there is a certain day of the week that doesn't follow your pattern, then your seasonality should be based off of the week rather than the day. Forecasting is the process of estimating future values based off of what we know. So let's say, just to be extremely simple, let's say we had the values 1, 3, and 5. We could propose that the forecast method would be something like y hat is equal to yx plus 2. And expected values are denoted with y hat. I think you can see there's a little hat on the y. All right. Now what I want to do is I want to go and cover each of the 3 parts of Holt-Winters so that you completely understand what's going on. So let's say we have this rather complex series in front of us. We might guess that a good estimate of the value that's coming next would be to go and calculate the mean. So let's come in and let's do that. The actual real value is close to 53, just to give you an example. All right, so that's what the simple mean would do. We could improve on this with a moving average that gets the average of the most recent values. So let's say we have mean, and we could say something like S1 and tail 2, or let's make it 3. All right, and if we run that, oh, it's np.mean, sorry about that, we get a value of 55. All right, so previously with mean, we got 57.2. Now we got 55. But guess what? If I go and mess around with these values enough, I'm going to be able to get a value close to 53. So that's just a matter of being accidentally lucky in making these calculations. We definitely want something better than the mean. So let's maybe say we wanted a weighted moving average. How we could do this is go and get an increasing percentage of the last 4 values, for example. And it's very important whenever you create your weighting that this is going to add up to the value of 1. So just come in here and keep adding these values together until we get 1. All right, so now that we have that, we can go and get the last 4 values in our series. So let's just go and get something like last 4, something like this, equal to 1. And let's go and get our tail. Last 4 values. There we go. Now we're going to have a moving average, which is going to start off at 0, of course, for I in range len, and let's get the length of our weighted list, ma plus and equal to, and go and get each of these individual parts and multiply them times the weighted list, like that. And then we would get a value of 57.6. Okay, so it's still not getting the exact value that we're looking at, but we're just moving on. And let me tell you, the data is going to make a lot of sense going from simple means to moving averages and so forth and so on. Now, one way that we found previously to get better results was to use single exponential smoothing. And that's what's going on here with Holt-Winters. We're going to start off, it's going to have 3 levels. So it's going to have single exponential smoothing, double, and triple. And with single exponential smoothing, we saw that it uses a weighted average across all of the data, set so that we have decreasing influence the older the data is. And of course, if alpha is always going to be between 0 and 1, that means that this is always going to produce a value less than 1. And anytime we would go and take the square or the cube of a value that is less than 1, it's going to decrease in value. And that's exactly how that smoothing works. So let's go and run an example. This is going to load our flight data that we covered previously. And this guy right here is going to allow us to make our calculation. So what we're going to be able to do here is we're going to be able to go and use this built-in function to get this smoothing effect. But one thing we're going to need to do is if we go flight df and index, we're going to see down here that it says frequency none. To perform these calculations, this cannot be frequency none. The most common frequencies that you are going to want to use are going to be something like business day, calendar day, weekly, month end, month start, quarter, so forth and so on. And what we're going to want to do is we're going to set our frequency to one of those things. Now, if we come in here and plot this information, here it is, there's all of our information. Based off of this, I am thinking that I am going to want to base the smoothing off of the months. So that's what I'm going to set this for. So I just go flight df and change this to index and frequency equal to dot ms. And then if I come in and do flight df index, you're going to see that the frequency is now set right there. And this would be the end of the month, ms. So what I want to do now is go and use that simple exponentially smoothing function we have. So I'm going to say model equal to simple exponential smoothing. And in the Jupyter notebook that I have on GitHub, I am going to show you another way of performing this, just to verify that you understand what we did in a previous video. But here I'm going to go and get this passenger's data, and we need to go and fit this in and define our alpha for this model. Model fit smoothing level is going to be alpha. And alpha, if you remember from last time, is going to be based off of, well, we're going to have span. The span of our seasons is going to be a year. So we're going to have our span be 12. Alpha, a good estimate of it is to 2 divided by span plus 1. All right, so we got that set up. So there's your alpha and where we get our alpha value. And then there's another thing that must be set, which is optimized. And I'm going to say that I do not want that optimized. And one thing that happens whenever we go and we apply this smoothing effect, which is what we did there, is it actually does the same thing twice for the first 2 rows. So we want to get rid of one of those pieces of data. So I'm going to say flight df, and I'm going to save this in something called single smoothing, SES, and equal to fit model dot fitted values and shift. And I'm going to shift the rows up by 1 to get rid of that 1 duplicate off the first row. And for homework, you can go and take a look at what that looks like. And if we run this, you can see here is our smoothing that is being taken place, and here is our real data. And if you go and compare it to what we did previously, you'll see that it is very similar. Actually, the results will be almost identical. And if we want to come in here and plot this to see what this looks like, there is the original data that we had, and here is our smoothing result. Alrighty? So I think you have a pretty good grasp on single exponentially smoothed data. So now let's move into double. Remember, in working out Holt-Winters, we're starting off with single, double, and then triple, and then we have Holt-Winters. All right, so I'm covering each part as we move up. Now, previously, we calculated y hat, which predicts one value. However, whenever we are predicting more than one value, this is going to be referred to as a level, which is going to use this L symbol right here. And of course, when graphing previously, we referred to slope, which would just be the difference in y divided by the difference in x. From now on, when we're using Holt-Winters, we're going to refer to slope as trend, and it is going to use this beta symbol. And this beta symbol is going to be used in much the same way as alpha was used previously. And another thing is, since we know that x will increase by a value of 1 for each element, we're going to just simply be able to ignore the changing values of x and focus 100% on the changing values of y. And what is happening with double exponential smoothing is it's applying smoothing to the level as well as the trend. And we're actually going to have 3 equations for calculating double exponential smoothing for both the level, trend, and forecast. And basically what this is going to create for us is a sloped line. All right? So let's come in here and I'll actually show you an example. What we're going to do this time is act as if our flight data is linear. So we're going to use the additive method, which I talked about in the last video. So I'm doing a little bit of review here. So exponential smoothing, and we pass in flight, df, and passengers, and trend is going to be additive, and we're going to call fit on this. And again, we're going to need to shift up our data because it creates a duplicate row. So I'm going to go and I'm going to call this one double smoothing, DES, and fit, and mod fitted values, shift, and make that go up 1 row. And if you just run the data flight df before you do this, you'll see what I mean. It creates a double row. Now we can come in and say flight underscore df passengers, as well as our smoothing. And what I want to do here is plot both of these at exactly the same time. And if you look at it, it looks like there's only the orange line on there. Remember, we printed passengers, then we printed the smoothing. It looks almost perfect. So it's not perfect, let me tell you. So what can we do here to go in and actually look at it closer to see how perfect it is? I mean, it's good, but it's not perfect. So one thing that we can do is let's just go and copy this. Or you know what, I'll just leave this here. And I want to just zoom in and look at the last 24 months. How I can do that? Just go dot iloc -24 colon and plot this. And whenever you do that, I don't know, it looks pretty good. I think you can see like a little line there. Okay, so that's how it's off. However, if we would come in and instead get the first 24, you're going to see that it's not quite as accurate. And there you can see now there's a gap. All right, and over time it's going to get more and more accurate. And there you go. Now I think you're seeing the power of being able to predict this data through just simple smoothing. Now to finally go and actually calculate Holt-Winters, what we're going to have to do is add in seasonality. Otherwise, it's not going to work. And what we're doing here with this first formula is we're going to smooth those seasonal values. And then we're going to use this guy to forecast future values. So we're going to smooth and then predict the future with these 2 formulas we have here. M is going to be a point somewhere in the future. And I already talked about what L was, and B, and so forth and so on. While L is going to, whoops, accidentally hit that twice. L in this situation is going to represent the divisions per cycle. So if the seasons is 6 days, then L is going to be equal to 6. And this is rather complex to explain specifics about what's going on here. So I'll leave it to you. If you want me to go in and talk about it very specifically, leave me a comment. But basically what I'm doing is estimating seasonal data based off of what happened previously seasonally. Then I calculate a new value based off of the level calculated up here that we so this guy. So what we're basically doing is this is providing an estimate of the function with the actual data. What this guy's doing is predicting the future based off of that past data. And as you're going to see, it's actually not as accurate as this, but this can't predict the future. Holt-Winters can. So let's go and get an example. I'm going to say flight df, and we'll call this triple smoothing. And this is exponential smoothing. Pass in again the flight data frame with our passengers data. And I need to pass in the trend is going to be based off of what? Well, we talked about previously. It's probably going to be additive. However, the seasonality is going to be multiplicative, and you signal that with MUL. And we also talked about what is our seasonal periods, what they're going to be based off of. Well, they are going to be based off of 12. All right, so we're going to have our 12 months. We're going to have our fit, and then we're going to have to say fitted values. And then we can say flight, df, and let's go and print out both of these at the same time. So what I want to do is get the last 24 of these results again, just like we did previously. And I want to plot them out. Fig size equal to, and we'll have it be 12 and 6. And this should be seasonal periods. And if I run it, you can see here is the orange predictions, and the blue is going to be the actual data. But you might say to yourself, well, wait a minute. If we just do double, it's more accurate than triple. Once again, this guy is going to predict the future. This guy isn't. And that is why the triple smoothing is so much better. And I think I've covered a lot in this video. In the next video, I'm going to go headlong into forecasting, and you're going to be quite amazed by all the things we're going to be able to predict. So like always, please leave your questions and comments down below. Otherwise, till next time.